Let's resume our next discussion. We are still within the world of algebraic equations. We talked about linear algebraic equations, single and systems. Today we will talk about single and systems of nonlinear equations. And my favorite is very large systems of nonlinear equations. So it's going to be really, really nice project with a large system of nonlinear equations. And putting everything all together, it all comes together. It all comes together, becomes one big happy family of tools. Okay, I will start with this problem. Just to motivate you. It's like a little silly problem, but still it motivates you a little bit for studying nonlinear systems. 26,000 gallons, so that's about almost 100 cubic meters of water. So, you know, what's a meter? I'm like a meter. I'm 2 meters tall. I'm like a meter. Well, I got 5'7". I'm like 1.68 meters. So, you know, about a meter. So 100 cubic meters, so cubes of 1 meter cube, 100 of them, of water has leaked into a municipality pipe, like these big pipes that they put underground. The pipe has a length of 15 meters, this is 15 meters long, and a radius of 4 meters. So cross section of the pipe, radius is 4 meters, so diameter is 8 meters, pretty big pipe. Find out if a maintenance person who's 5'7", that's me, okay, so 5'7" or 1.7 meters tall, can walk through the pipe to investigate the damage without being submerged in water. Okay, so there's a 15-meter long pipe with a given diameter. It's circular, the water spilled in, and it spreads up to a certain level or height h. Now, if h is larger than 1.7 meters, this maintenance worker is not going to work. We need to call the Globetrotters or the NBA to just bring us some taller people. Or, you know, they might be able to just go in because, so our purpose is to find h. Okay? Now, so this is these are two cross sections of the pipe. So this is a view through the cylinder, and then if you cut the cylinder in the middle, okay, so like this is the entrance of the pipe. It's going to look like a rectangular cross section, right? We slice it in the middle. This is the person walking, and look, they're looking like, what's happening here? Where's the damage, right? They have a flashlight, okay? And now the equation for the water. Now this is a fun exercise to actually derive this equation. Like you spill a volume of water, how is it going to spread in a cylinder, right? So what is the relation between the volume and the cylinder radius, and what is going to be the height, etc. But we have the formula for you. So if a volume of water V that fills up a hollow pipe of radius r and length L, this is the equation for that. V, the relation between V, L, and the radius and the height of the water is given by this complex formula. It says, so V here we have 98.4 cubic meters. We know L is 15 meters. We know R is 4 meters. What we don't know is h. So we're trying to solve this equation for h. Okay? H is the maximum height of the water in the pipe. Now to answer this question, we must know the height of the water, h in the pipe. If h is less than 1.7 meters, then the person can, well, we want it to be, we don't want the water to be here. Like we want it to be maybe less than 1.5 meters, right? So that they can walk comfortably. And then there's a rat swimming and splashing water, and they're like, ew, it's gross. So I don't know if rats will live there, but maybe going for a swim. And then L is 12 meters long. Now, if h is less than the height, then the person will be safe to go in the water, etc. Okay, so can you solve this problem by hand? Go find h. You can try to do manipulation, but it's not going to work. What do? You take the square of this to get rid of. I don't know. You know, I don't think you can solve it by hand. And the true answer is like, yeah, this is unsolvable by simple algebraic manipulation. It's just simply not solvable. Okay, very nonlinear equation in H. Now, if I taught you well, then you realize that V and L show up linearly in this equation, but R and H show up nonlinearly, right? Because both R and H, they're either under a power or a transcendental function. You have the R cosine, and you have the square root over there, and you have the squares, etc. So it's a very highly nonlinear equation in H and R, not in L and V. Okay, so we know how to solve linear equations. We know how to solve systems of linear equations. In this chapter, you will learn how to solve a single nonlinear equation and systems of nonlinear equations. So in systems of nonlinear equations, we'll talk later, you have two or more unknowns that show up linearly, and you want to solve them together. Now, what is a nonlinear equation or function? Well, it's the opposite of a linear equation and function, which we defined last time. So now we will define a nonlinear equation as one where the variable of interest, this is very important, is you have to determine, like in this previous equation, we had V, L, R, and H. What are you solving? What's your variable of interest? If your variable of interest is V, well, it's linear. It shows up linearly. If your variable of interest is L, it shows up linearly. But if your variable of interest is R or H, that's what you're trying to extract from that equation, then those show up nonlinearly. Now, you can say the equation in general is it's a highly nonlinear equation, but what you're solving for, the variable of interest, does it show up linearly or nonlinearly? I like to use this unambiguously and unapologetically. Say, okay, V shows up linearly, R shows up nonlinearly. Okay? So, for example, in this equation, how do A, R, Q, and H show up? So A, does it show up linearly or nonlinearly? Nonlinear, right? You got the A squared, and you got square root of A over here. R shows up linearly, right? Q, linear. H, nonlinear. Although H here shows up linearly, but there's a cosine H here, which is nonlinear. That trumps everything. Okay, good. Now, what does it mean to solve an equation, or say f of x equals 0? Whether the equation is linear or nonlinear. Okay? And I'm using x here as a generic unknown. Okay? So this f could be a very highly nonlinear function in x or a simple linear function in x. So what does it mean when we say we want to solve f of x equals 0 visually? So the way I like to think about it, if I know f of x and say it looks like this. This is a function in x on the x-axis, y-axis. It looks like this. It's going up and down. It's highly nonlinear. When I say f of x equals 0, it means you're looking for the points where f of x intersects the axis or the value y equals 0. So if you draw the line y equals 0, the intersection points of f of x and y equals 0 are the values that you're trying to find when you say solve f of x equals 0. So when I tell you solve f of x equals 0, it means find me those points where f of x intersects the line y equals 0, or the line at y equals 0. Okay? So solving an equation f of x equals 0 means finding the values of x, make f of x 0. Those values of x are called the roots of the equation. They're also referred to as the zeros of the equation because they make the equation equal to 0. It's a simple intersection. Okay, let's do some exercises together here. So first, I'm going to give you this blue curve visually, and this blue curve that's intersecting y equals 0. So visually locate the root. Where's the root? Just about here, right? That's the root. Okay, good. Great, there you go. There's an arrow and a red point if you didn't see it. Okay. Okay, so now I have another curve also in blue. It's given by this blue curve. Call it f of x. Now I want to solve f of x equal 10. Okay, so how did you get that? At what? At 10. Okay. So in this case, we're intersecting the function f of x with the line y equal 10. So if you draw the line y equal 10, okay, this is the root in this case. F of x equal 10. You're intersecting f of x with the line y equal 10. Okay, so the root of f of x equal alpha is the point of intersection of f of x and the horizontal line y equal alpha. Okay, so now keep this in mind. Just going to bring it down here. Now I have another function, which is the same f of x, but now I have f of x minus 10, and I call that r, a new function, r of x. What is the root of r of x equals 0? The same, okay? And you intersected r of x with what line? 0, okay? So it's the same one. Okay? What I did here, I took this condition, f of x equal 10, I moved 10 to the left-hand side, okay? And I called that a new function, r of x, okay? And then asked, well, the root of f of x equal 10 was equal to the same root as r of x equals 0. Okay? So this is called, this procedure of moving everything to the left-hand side is called the residual form of an equation. Why do we do this? Because we want to standardize our discussion about nonlinear equations. We want all the nonlinear equations, all the roots to be the intersection of the function with y equals 0, period. That's simple. Because you don't have to, oh, what are you intersecting? I'm intersecting it with 11.5, 7.6. No. Just residual form, put in residual form. Always we're intersecting the function r, the residual form, with the line y equals 0. Okay? Simple. That's called the residual form. This is the form we will work with. Now compare this to linear systems of equations where all the constants or the known values, we move them to the right-hand side. So we have unknowns and knowns. With nonlinear systems, you move everything to the left-hand side. Okay? You move everything to one side. You can move the right-hand side to the left. So 10 minus f of x or f of x minus 10 is going to give you the same root. Okay? It doesn't matter. All right? But that's the standardization we're talking about. So now, we're going to come back to this because we want to solve this together. What is the residual form of this equation? What is the residual? Move everything to one side. Either move v to the right-hand side or move all of this to the left-hand side. That's it. Any one of those will work just fine. So then I define my residual function, and now because I'm solving for h, because I'm assuming v, l, and r are given to me, okay? So my residual is strictly, I'm looking for h. That's my variable of interest. I moved everything to the left-hand side, so my residual function is v minus all of this guy, l, r squared, etc., equal to 0. So now my root is the intersection of all of this, v minus l, blah, 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 with the line y equals 0. Very simple. Okay? Otherwise, we would have said, okay, the root is going to be the intersection of this with the line y equal v, 98.4 cubic meters. Right? But what if you change? Well, this standardizes everything. Function with the line equals 0. That's it. Okay. So next, we're going to just hit the ground running. I'm not interested in teaching you the theory of how to solve this equation numerically. So you can go back to my numerical methods lectures on YouTube if you want to dig into the details. I don't think you need that. You might have seen it. That's great. If not, what I need from you is to know how to solve a nonlinear equation. Okay? And if you do, great. If you don't, this is the opportunity to learn it. So Python provides a lot, like any code, useful code base like MATLAB, Python, they need to have built-in root solving routines, and they do. Python has a great routine coming from scipy.optimize. So now, what is scipy? They all end with pi, right, for Python. So NumPy is numerical Python. Scipy is scientific Python. And interestingly, NumPy didn't own nonlinear solvers. I guess it was too hard for them. So scipy decided, I want to own, the people at scipy who designed scipy, they want to own nonlinear solvers, and they do. They have all the best routines to do nonlinear, to find the roots for nonlinear equations. So scipy is a big library. Inside that library, there's the optimize module. So scipy.optimize offers a collection of nonlinear solvers. You probably heard of fsolve in MATLAB and Python in the past. The newest version is called root, simply root. It's a routine called root, routine. That's pun joke there. Couldn't help it, but okay. So you can use the root routine from scipy.optimize. So you simply say from scipy.optimize, import root, or you can say scipy.optimize.root to call that routine. And the way you call it is simple. You say solution, or my root, equal to root. You're going to give it at least these two parameters. Whatever comes here, we can talk about this later. Excuse me. But you have at least two parameters. What are those parameters? The first one is a Python routine that implements your residual function. Okay? Now, what does that mean? You're not going to put the routine here. You're going to put the name of that routine. So if your routine is called my residual function, you define it somewhere in the code, you implement the residual function, all you have to say here, my residual function. Python internally goes and assumes that this is the name of a Python routine and just calls it. Okay? By definition, the first argument in this Python routine of the residual must be the variable for which you want to compute the root. So if we go back to the v minus L cosine inverse, etc., h, r, and whatnot, your first argument in your residual function is h, because you're solving for h in that residual. Now, you might have other arguments, where we will worry about this later, but at least that function here, that residual, you need to be able to call it and give it a value of h. Why? Because inside root, and if you've done the Newton solver with me, inside root, you are going to repeatedly call that residual and check if you actually found the root. Because when you find the root, the residual is 0. So how do you check? You call it over and over and over and over again. Okay, and you keep checking until you find the root. For the root function, you also need an initial guess. Okay, and this is where the nightmares start. How do I get my initial guess? And simply, I don't know. Actually, you know. How do you know? Because you're going to be an expert in your field. If you're doing, I don't know, growth of bacteria and like bacterial, how many babies they have, or whatever, lobsters, or whatever you're studying, okay? And so you know at least where to start. You say, let's say you're solving for the growth rate of bacteria, and you have an idea that these bacteria, you know, double every hour or something, right? And then you have a guess, you have an idea of where that starts, but this new bacterium might do, you know, 2.5 an hour. So maybe start at 2, because you know your system, your setup, okay? You have an idea of where that is. In other situations with large systems of nonlinear equations, like in fluid dynamics, heat and mass transfer, etc., usually you're going from one time step to another, to another, to another. You're moving one little step at a time. Your initial guess is simply the solution from the previous step. Okay? That gives you your initial guess because you're not moving far away from the previous situation. Okay? When you have only one nonlinear equation and one unknown, you can figure out where the root is simply by plotting the residual function, which we will do just to give us an idea. But anything beyond that, 2, 3, 5, 10, 100 nonlinear equations, you're in the dark. You have to rely on your expertise. Or, like for example, if I'm solving a nonlinear heat transfer problem, which you will solve in your project 1, and I have temperatures at both ends, well, I guess the temperature is my initial guess is going to be the average of these two temperatures. And then see what happens. It's going to depart a little bit higher, a little bit lower than that average. But that would be my initial guess, and it's quite reasonable. Okay? Now, sol, that variable, that root, returns something. We're going to store it in sol here, or just for the sake of the argument. This sol is a Python object. Don't worry about what that object is. You can dig into it. It's just a storage container that contains information about your solution. So once we see this, you're going to see sol is going to print out, did I converge, what's my error, how many function evaluations did I do, etc., including the roots themselves, the values of the roots that you're interested in. Okay? Now, to access the root, you do sol.x. Sol.x gives you the value of the root, or the roots when you're doing one or two or more equations. Okay? So to summarize, this is my setup. Here I have v equal L, etc., and I have my residual function. So let's go ahead and do this together in class and solve for h and see if the 5.7 maintenance worker can go in and inspect the damage. All right? Let's grab a Jupyter notebook. So I'm going to move the slide over here. Okay, so we know what we're implementing over here. And let me grab a new notebook. And some of your colleagues wanted to use Google Colab or the Anaconda Cloud. I don't care. Whatever, as long as it's a Jupyter notebook or even a Jupyter Lab, that's all acceptable. I want to see, as long as I can see the math and the plots with markdown and discussions, I don't mind. Okay? All right, so let's call this Fall 2025. Okay, pipe flooding. Nonlinear example in class. Okay. All right, so let's grab our boilerplate from here. What I will build this year is a little cheat sheet, or a big cheat sheet of these, everything we've learned in Python, like import NumPy, we learned algebra.solve, numpy.diag, all of those things. They're really, that's in your tool set, and that's pretty much most of what you need, with the few things that we're going to learn next, and that covers a lot of the things that you can do, that you need to do with Python. So just copy and paste this. That's going to be my boilerplate, and let's just put it here. Okay. Now I also want to import SciPy. So from SciPy.optimize, import root. No, you can directly import one routine from whatever module you want. If you import all of SciPy, you're adding more memory load on your notebook. As if you only need one routine from NumPy or SciPy, just import that. Okay, NumPy, I import all of it because it's the most used for pretty much every function. Now, NumPy and SciPy work really well together. So SciPy takes NumPy arrays, etc. So it assumes that. So that's kind of why NumPy import the root finding routine. Ha ha ha. Okay, I had to do this, and nobody laughs. It's like, thank God for my kids. They still laugh, right? At this age. Oh, my son has a message for you. I recorded it, but. I wish I had this big speaker here. He said, Papi, give them a very easy homework so they don't learn anything. So I sold him the message. He's like, Papi, why is our homework so hard at school? He's like, in kindergarten. I'm like, well, because you learn. And I turned to my wife, like, it's insane. It's so much work. We're spending like an hour for a kindergarten kid. So he kind of apparently accepted that story. And oh, man. OK. Let's see. You guys in the back, OK? OK, how about this? All right. So next, I want to implement this this routine, this residual. Not routine. OK. I want to implement this residual function. OK. I'm going to say define pipe residual. And like I said, by default, by definition, by requirement, this residual function needs to have at least one argument and the first argument needs to be related to the variable of interest you're solving for. So in this case, it's going to be h. I'm going to call it h, not x or anything else, because I want my code to look exactly like the math that I'm implementing here. All right, so move this over here. And let's say, OK, I'm going to store this in a variable called result. I'm going to do v minus l times r squared times, where do we get the r cosine? Let's get it from numpy. You can get it from math, but if you're dealing with arrays, which might happen, you might have a residual function that looks the same, but with arrays, math is not going to work. Math.r cosine is not going to apply on an array, so it's better to just grab it from numpy, arc cosine, all right? And then open parentheses, and I need another parentheses, r minus h over r. Is that correct? Okay, minus r minus h times mp dot square root, again, open parentheses, 2 times r times h minus h squared. Okay, and then I close the parentheses. That's my residual. Now you're going to tell me, oh, where did v and l come from? Okay, let's declare them globally. Let's declare them globally. V is equal to 98.4 cubic meters. And then LR is what? 4 meters radius. Okay. Volume of spilled water. Okay. And then L is equal, what, 12 or 15? I think one time I used 12, one time I used 15. Let me see, what did I put here? 15 meter. Okay, let's do 15. Pipe length, meter, pipe length. Okay. Now you say, oh, Professor Saad, why don't you put these over here in the pipe residual so we can just pass them on? We will do this in a little bit. Right now, just start simple and just define them here. Now, this function here, inside it, this Python routine, inside it is going to see this v, is going to see this r, is going to see this l. Okay, that we define. Okay, and then for my residual, all I have to do is return result. That's it. Now, what is going to happen mechanistically inside Python, inside the root finding algorithm, is going to call this pipe residual and pass a value of h to it. So once it calls it, it has everything it needs. It has v, l, and r, and h coming in. It evaluates it. It returns a value and checks. Is that value close to 0 or within tolerance? Should we stop or not? Okay. So now, before I call the routine function, let's get familiar. This is a 1D nonlinear equation, one unknown. I can just plot the residual and eyeball the root and choose an adequate initial guess and see what happens. So let's go ahead and plot this. To plot this, I know v, l, and r, so those are fixed. I need to plot with respect to h, so different values of h. Okay? Different values of h. Okay. All right. So let's define a linspace. mp.linspace. And let's say, from h equals 0 to h equal 10, right? Because that's or h equal 8. So the range of h values is 0 to 8 because that's the highest, that's the pipe diameter, correct? So I'm going to create a bunch of point values here, 50, 100 points, and plt.plot x pipe residual x and plt.grid. Name v is not defined. Result name v. Oh, I didn't execute this. Okay. Okay. So this is my f of x. Where's f of x equals 0? It's right here. Right? So it does cross the x-axis. Okay. So let's put a line there, PLT dot horizontal line, axis horizontal line at y equals 0 and color equal black. Okay, so this is going to be, this is where my root is. And this is good news because this residual function does have a root. It has a single root, and it's located around this height. The height is what? About, oh, it's almost 1.5 meters. Okay, I don't know exactly what it is, but that's what the root algorithm is going to find for us. Okay, but at least I visually eyeball it. So, you know, I can start my initial guess at h equal 1 or h equal 3. It is going to find it. Or h equal 4, it's going to find it. Right? So let's see how this works numerically. So we will call the root function sol equal root. And when you call root, it's just going to give you, and you open parentheses, shift tab, it will give you all of the options that the root algorithm takes. Fun is, it's not fun, it's a residual function. X0 is the initial guess or guesses. If you have more than one equation, see this, find a root of a vector function. So you could have 1,000 residuals here as a vector. So your initial guess, you need a vector. Args, we'll talk about this in a bit. Method, this is the subroutine that finds the root. Again, you don't touch that for now. You're not going to need it in your homework assignment. I might ask you to use another one. But this is technically, you know, if you know Newton's method for hybrid, Hyber is a hybrid algorithm that uses Newton's method with some other kinds of approximations with it. There are other nonlinear solvers that are suitable for other kinds of problems. But if you don't touch these, this just works just fine. Okay? So what I will do is now give it the name of that residual. It's pipe residual. That's all I need. Don't put parentheses or anything. Python will assume that this is the name of a Python routine, and it will just call it. And let's give it x0. x0 is equal to, I don't know, let's put 1.0 for the height. And then it ran, okay? Let's print it, print sol. If you print sol, it's going to give you a bunch of things, because sol, again, is an object that contains information about the solution. There's f Jacobian, function value, the solution converged. Oh, great. N f, that's number of function evaluations. How many iterations did it take to converge to the solution? So how many times did it call back that pipe residual? So if you know Newton's method, this is how many iterations it took. And then you have your bunch of other things. I don't even know what they are. And then finally, x is your root. X is an array that contains one value, which is 1.5 meters. And then you can say print sol.x. That will give you the root. So the height is 1.5 meters. The inspection worker is 1.7 meters tall. So they can go in. I'll be fine. Okay, they're going to be just fine. Okay? Finding a root for a single equation, not that hard. Especially that you can plot your residual function. Good? Great. Let's proceed. Okay. Now, sometimes, like in this case, some functions have arguments or parameters, like v, l, and r in this case. What if I want to try all of these heights, find different heights with different combinations of v, l, and r? You might say, oh, well, you know, we already declared them as global variables. But that's, again, using Python as a computer. What ideally you want is to have an encapsulated routine that takes in all of the parameters, additional arguments to your residual function. You're still solving for h, but I also want to pass v, l, and r as arguments. Turns out that root allows you to do that. So what if my residual function looks like this? X is my variable of interest that I'm trying to find, in this case h. What if I have a bunch of other things, a, b, c? You could have 50 arguments over here. Okay. Well, you can do this from root. You call my residual, give it the initial guess, But then notice here what you do. There's this additional option in root called args, where you give it the arguments, the additional arguments to your residual function. Note how those match exactly, and they go exactly in the same order you declare them in your residual function, okay, in your residual routine. So let's try this. So my next step is going to be, I want to declare another pipe residual function, def pipe residual with args. I'm going to do H, I'm going to do V, L, and R in that order, okay? And it's going to be the same thing here. But in this case, when I call this routine and give it V, L, and R, this routine, this V, L, and R are going to correspond to these, not these, because local scope of a function of a routine precedes global scope. So when the pipe residual with args comes here, and I'm passing it these arguments, it's going to put these values over here. Okay, so we can try this. Again, I'm going to use the same values just to verify. So let's do this. Sol2 is root. Let me, okay. Root, pipe, residual with arguments. And I'm going to give it x0 equal 1.0. And now my args are going to be equal to, like I said, in that order, V, L, and R. So V, I'm going to put 98.4. And L, I'm going to put, what did we do, 15. And R is 4. So the same conditions as before, because I want to verify that this is going to give me the same root. And then print sol2.x. Indeed, it gave me the same exact root. Except here, I had everything predefined up there. But now, with the args, I can change the arguments right over here. Or what if I had a function where I'm looping, right? It's just easier to change it in line. So what if now we spilled, 120 cubic meters? Then, the height is 1.72. The person cannot go in. What if we spilled 30 cubic meters? So the height is almost half a meter. Let's go back to 100 cubic meters. What if now the length of the pipe is shorter? Okay, well, then the root is, see how fast this becomes when you pass the arguments in line through your routine. Okay? Easy, piece of cake. Okay? Tool, we're not going to learn the techniques. If you want to learn them, again, go to my numerical methods lectures, and you'll learn a lot. I had a little snippet here from a film. I like to try to find math and science stuff in movies and see where they botch it or where they get it right. In my previous class, I used to have a big microphone with speakers so people could hear. This is one about the method that is used to inside root, one of the methods, and it's called the Newton-Raphson method or Newton's method. Okay, it's from a film about gambling. I'm not a gambler, neither you should gamble, but there's a lot of math in games of chance. It's really fascinating stuff. So this is a film called 21, Kevin Spacey and a bunch of other guys. Let's see. So they go and game casinos. If you haven't watched it, you should. It's a good movie. Okay. Oh, okay. I don't have the. Hold on. Let me set the sound. Okay. Let's see. Output. It should be my MacBook. Okay.
All right. Now, who can explain Newton's method and how you use it?
You can use it to solve nonlinear equations.
That's impressive. That's really good. I mean, I'm very impressed by that, especially since my class is called Nonlinear Equations. All right, now somebody tell me something I don't already know. Anyone? Bueller. Anyone? Bueller.
Newton stole it.
I'm sorry?
Newton stole it. Joseph Raphson published the same method 50 years earlier. If the start value is too far removed from true zero,
The initial guess,
it fails.
it's going to fail.
I'm sorry. What's your name?
Ben Campbell.
Ben. So Ben Campbell suggests that Joseph Raphson was the original author of this method. Well, if that's the case, then why didn't he get any credit? Well, for one thing, Newton had a better publicist. And for another, after 1700, we know very little about Raphson.
Okay, so pay attention to what Ben said. If the initial point is away from the true zero, the method will fail. So that's your initial guess. If your initial guess is far removed from the true zero, the method will fail. There are other issues with Newton's method. If you can get stuck in local minima, you can just get stuck in there. So if you choose your initial guess in a local minimum, you're going to keep it's not going to converge at all. Okay, that's some of the risk of initial guesses. All right, with that, I'll let you go. Have a nice weekend. Godspeed. I'll release a homework assignment today. I wanted it to contain a system of nonlinear equations, but apparently we didn't cover that. But we'll do that next week, okay? And we'll see you on Tuesday. Thank you. Please don't forget to fill out the survey.